Okay, so calculating delta G, standard change in free energy for the reaction, that's the criteria for spontaneity at standard conditions. There's 3 different ways we can calculate this. We can calculate delta H and delta S from the heats of formation and the standard entropies, and then we can plug those values into this equation. We can calculate delta G directly from the change in free energy for the formation of the substance. We can also calculate it from free energy changes for the steps in a stepwise reaction. There's 3 different ways, and which way you use is going to depend largely on what kind of information that you have, right? So we do need to know how to do all 3 ways. Because if you don't have if you don't have delta HF and you don't have S0 for the things in your reaction, there's no way you can do this one. If you don't have the free energy of formation for the substances, you can't do that one. Okay? If you don't have any stepwise steps in a stepwise reaction, you can't do the last one. So using delta G equals delta H minus T delta S, we can calculate delta S0 like we just did an example of from tabulated values of standard entropies. We can calculate delta H0 from tabulated standard enthalpies of formation. They both have the same form where you take the products and you subtract the reactants. So for delta H, just change the S's to H's. So that's kind of nice because you don't have to learn another equation. And being able to remember that delta is always final minus initial can help you out in a situation, say on an exam, where you're like, I don't quite remember how that went, right? It's a change in, it's whatever it ends up in, the final situation minus where it started from. So after you calculate these 2 values, you can plug those numbers in here. Now, this is really only valid at 25 degrees Celsius because these are standard enthalpies and standard entropies, right? And those are defined at 25 degrees Celsius. But it's still going to give us a good estimate at other temperatures. So we're not going to get too fussy about that. Okay, consider the oxidation of NO to NO2, calculate delta G at 25 degrees Celsius and determine whether the reaction is spontaneous at this temperature. The title of this exercise says we're supposed to calculate that using delta G equals delta H minus T delta S. So what that means is we need to find out what's delta H for this reaction. We are conveniently given the information that we needed. Here we've got our heats of formation and we've got our entropies, which I think that should just be S. Yeah. That's not delta S. So we need delta H. So let's calculate that first. So the standard enthalpy of this reaction is going to equal the heats of formation of the products minus the heats of formation of the reactants. So we're going to look at the product. There's only one. And these are kilojoules per mole. We need to multiply by moles. So this one, there's only 1 mole. So this is 1 mole times 33.2 kilojoules per mole. And that's the only product. Now we're going to subtract the reactants. We've got no, and so that is 91.3, and there's 1 mole of that. Plus, we have half of a mole of O2. Sometimes you are given information, you're like, wait, they didn't tell me what this one was. Well, this is an element in its standard state. It's a gas at room temperature, and so its delta H is 0 because we decided that was where we were measuring 0 from. Okay, so then that's times 0. And we can calculate delta H. So negative 58.1 kilojoules. Units are important. Any questions about that one? So then we have 1 mole of product, that's the NO2. So we look up S for that, 240.1. Joules per mole Kelvin. Only product, so that's the first thing. Then we're subtracting the reactants. 1 mole of no, looking at the wrong column, 210.8 joules per mole Kelvin. Plus half a mole of oxygen. The entropy of oxygen here is not 0. We're never going to have 0 entropies. So this is times 205.2 joules per mole Kelvin. So 240.1 minus the quantity, 210.8 plus 0.5 times 205.2. Getting negative 73.3 joules per Kelvin. Did I make any mistakes yet? That might be a new record. Okay, so we've got those numbers now. Now we can use this equation. Oops. So I'm going to change the color, and I changed it to the same color I had been using. So delta G for this reaction is delta H minus 58.1 kilojoules minus the temperature. Well, this is at 25 degrees Celsius, right? That needs to be in Kelvin. That's equal to 298 Kelvin. So we've got 298 Kelvin times delta S, negative 73.3 joules per Kelvin. These kelvins are going to cancel out. But this is the problem that shows up over and over and over again, where we've got one thing in kilojoules and one thing in joules. And so we need to convert one or the other. I think at this point it's just a lot easier to convert this one, because we can do that by just scribbling that out and saying, well, that's the same as times 10 to the third. So negative 58.1 1 times 10 to the third EE3 minus 298 times negative 73.3. And that's what my calculator is giving me. Is joule the best unit for that big, big number? No. So if we put it in kilojoules, that's me negative 36.3 kilojoules. Any questions? So that's delta G. Determine whether the reaction is spontaneous. Is it spontaneous? Yeah. Delta G is negative, so this is spontaneous at this temperature. Yeah. This is times 10 to the third. Yeah, and you're right, that looks a little wonky. Let's see if I can fix that. There. Yeah, thanks for pointing that out. Because, yeah, multiplying by 103, what are you doing? I don't know. Any other questions? Just make sure I didn't skip anything. I didn't skip anything. Estimating the standard change in free energy for a reaction at a temperature other than 25 degrees Celsius. This is not the best calculation. It's not going to give us a real strong, accurate answer, but it's going to give us an estimate, which is a lot better than having no clue. So for the reaction in that practice question we just did, calculate the value of delta G at minus 55 Celsius. And then, is this more spontaneous or less spontaneous at this temperature? So to save us from jumping back and forth, I put in here delta H and delta S that we already calculated. So to calculate at this different temperature, we're going to use delta G equals delta H minus T delta S. Delta H and delta S are going to be the same numbers, but T is going to be different. So T is negative 55, so 273 minus 55, so our temperature is 218 Kelvin instead. I'm just going to write the times 10 to the third instead of joules. And now we've got 218 Kelvin times negative 73.3 joules per Kelvin. So I converted this one to joules already. So that's delta G at this new temperature. More spontaneous or less spontaneous? Is it more negative or less negative than it was before? it's more negative. It was 36. So it had been minus 36.1 at 298, and it's minus 42.1 at 218 Kelvin. So it's more spontaneous. Any questions? We can also calculate delta G using free energies of formation that we can look up in a table. The free energy of formation, delta G with the degree symbol, F for formation, the change in free energy when 1 mole of a compound in its standard state forms from its constituent elements in their standard states. The free energy of formation of pure elements in their standard states is 0. Delta G behaves a lot like delta H. Elements in their standard states, 0, right? If you're looking at something else, you're looking at either the change in enthalpy or the change in free energy for forming whatever that is from the elements in their standard states. And many, many people over the course of many, many years have measured all of these things, and so we can just look the numbers up in a table. So elements have free energy of formation equal to 0, the same form of equation here as we used for delta S and delta H. The sum of the products minus the sum of the reactants. So now we have a table that's giving us delta G. When you look at the table in the appendix, it's got delta H, S, and delta G. 3 different columns, so just be careful to get the right column. One of the reactions that occurs in a catalytic converter is we have the oxidation of carbon monoxide, the reduction of nitrogen monoxide. Both of those are harmful pollutants. And so we can take these pollutants and convert them into CO2 and nitrogen, which are both normal components of air. Use the standard free energies of formation to find delta G for this reaction at 25 degrees Celsius. Is it spontaneous under standard conditions? So delta G for the reaction is going to be the sum of the moles times delta G of formation for each of the products minus the sum of the number of moles times delta G formation for the reactants. Products minus reactants, final minus initial. So the final, we have 2 moles of CO2. I'm going to leave the CO2 off. So we're going to look at what is delta G for CO2 and make sure that it's the correct state. It is, so minus 394.4. That's kilojoules per mole. Then we have to add 1 mole of nitrogen. Well, what's the standard free energy change for nitrogen? It's 0, because that is the element in its standard state. And like enthalpy, this is where we define what we define as 0. So this would be 1 mole times 0. So that's our products. Then we're going to subtract the reactants. We got 2 moles of CO, CO minus 137.2 kilojoules per mole. The math is not hard in these calculations, but there's a lot of pieces, right? So you really should write this down. I don't care if you write down the actual equation, but write it down with the numbers that you put in. So you can check that the units are going to work out. And so if you get the wrong answer, two easy things to check are just type it through in your calculator again, because maybe you just punched a button wrong. And if that doesn't work, then make sure that you picked the right one and that you copied all the digits correctly, because that can mess you up as well. So 137.2, and then we have 2 moles of no, and that has NO plus 87.6 kilojoules per mole. So 2 times negative 394.4 minus the quantity 2 times negative 137.2 plus 2 times 87.6 negative 689.6 kilojoules. All these moles cancel out. Yeah.
For the spontaneity of it, could you always just look at the original equation and see that since moles are decreasing, it's always going to be?
That's a great question. Could you just look at this equation and see, well, this is 4 moles of gas to 3 moles of gas, and just say, oh, well, that's going to be whatever? No, you can't. Because we can predict the entropy change for this. Going from 4 moles to 3 moles, the entropy is going to go down, right? So that's going to be a negative entropy change, which would suggest that it's not spontaneous, right? But when we calculate delta G, we see that it actually is spontaneous. And that's because you've got delta H and delta S are both playing a part in there, and then there's the temperature dependence. That's a great question. So we've got a negative delta G, so this is spontaneous. Any other questions? Okay. Calculating delta G for a stepwise reaction from the changes in each of the steps. This is the same process we did with delta H in Chem 1A. So free energy, like enthalpy, is a state function. So we can calculate the change by looking at the free energy changes for the steps in the reaction. Hess's law says if you add up all the changes in the steps and the steps add up to the overall equation, then those changes will add up to the overall delta G. So same relationships as for enthalpy. And so if we're doing something to the chemical equation, we do the same sort of thing to delta G as we did to delta H. If we multiply the chemical equation by a factor, we double, say, all of the coefficients, then we're going to multiply delta G by the same factor. Because if you have twice as much stuff, the free energy change is going to be twice as large. If you reverse the chemical equation, then you change the sign on delta G. Because if going forwards was spontaneous, was negative, going reverse is going to be the same number, but positive. And we can add steps together. Any questions? We did something similar to this when we were talking about equilibrium constants, but the equilibrium constants are like elevated in terms of the operation. So for For equilibrium constants, if we multiplied by a factor, then we raised it to the power. And if we reversed it, we didn't change the sign, we inverted it, 1 over. But delta G and delta H behave the same. So that's nice because there's less to remember. Okay, find delta G for this reaction. We're given the steps and delta G's for the steps, and so that's the method we have to use here. You know, if you were just loose in the world and you needed to know this, you could just go and look up the values and that might be faster, right? But that's not what we've got going on here. I think it's helpful to highlight with color so that we can keep track of what we're looking at here, because there's N's and O's all over the place. So N2O, okay, see, I already made a mistake. This is N2O, that's not N2O, that's NO2. Okay, erase that. This is NO2, that's NO2. And then at the end here we have no, favorite molecule. That's no, and no also shows up in here. When you're identifying these things, each of the reactants and products should show up at least once in those stepwise reactions, and each stepwise reaction should have one of those things in it. So now what we have to do is we have to figure out how can we add these three things together to get that. There's different ways to approach that. I like to just start at the beginning of this one. I need N2O as a reactant. So I'm going to choose this equation. It has N2O as a reactant, and so I'm going to write that down. So 2N2O forming 2N2 and O2, and delta G is negative 207.4 kilojoules. I'm being lazy and I'm leaving off the superscripts and the subscripts there. I took this chemical equation, I copied it down exactly the way it was, and so delta G doesn't change, it's the same. So there's my N2O. I need NO2 also to be a reactant. NO2 only shows up in this one. So I'm going to use this equation, but here NO2 is a product. I need it to be a reactant. So I'm going to write that equation backwards. 2 NO2 making 2NO plus O2. And again, I'm going to go in and highlight. So there's my NO2. And this also had the NO, which we were using blue for. So that's in there. I wrote the reaction backwards because I need NO2 to be reactant. So what do I do to delta G when I reverse the reaction? We're going to make it positive. We're going to change the sign. So it was negative 71.2 kilojoules. Because we're putting it in the opposite direction, it becomes positive. I'm not paying attention to coefficients yet. I'm just trying to get the molecules or the chemical formulas in the right place. So here we've got N2O and NO2 as reactants, and we've got NO as a product, but we also have these other things in there. And that's why there's a third equation here. We need those to get canceled out by something, and this other equation is what's going to cancel them out. So this already has NO in the products, and so I'm going to write this one down just the way it's written up there. And I didn't do anything to the equation, so I'm not going to do anything to delta G plus 175.2. So let's try adding these together and see what's going to work or not work. I'm going to end up with N2O and NO2 on the reactant side. I'm going to end up with NO on the product side. So what I want to do is look at these guys and make sure they're canceling out. I've got one nitrogen over here and two nitrogens over there. There's a couple different ways you could do this. What seems the simplest here is, well, let's double this reaction, because I need two N2s to cancel those. So I'm going to multiply that by 2, and this by 2, and this by 2. And when I do that, I also multiply this by 2, because I've got twice as much. So the free energy change is twice as large. Now, does that help things? Well, I have two N2s and two N2. So those are going to cancel out. Here I have an O2 and another O2. That's a total of 2. And over here I have 2. So those are going to cancel out. So then I can copy down what's left. Okay. I took these 3 chemical equations, I crossed off the things that appeared exactly the same on both sides, and I added them together. I'm adding these together. I'm also going to add the delta G's together to find out what delta G is for this reaction. So I've got negative 207.4 plus 71.2 plus 175.2 times 2, and I'm getting 214.2 kilojoules. Well, this is great. Does my reaction here, my equation, match exactly with what we have up there? No. It's doubled. We could have avoided that by cutting some things in half as we were going through here. You know, and for some people that makes more sense. I decided I was just going to deal with it at the end. So this is twice as big as we need, right? We need 1, 1, and 3. So we need to divide each of these by 2. So here's a question. Why would we want to do something like that? Nobody does it just for fun. Pardon me? So we can know how to do it, but why is it important to know how to do this? In case we're not given other pieces of information, right? If this is all we've got, this is the only way we can calculate this. right? Another thing is, it's like, well, you could do an experiment and actually do that reaction and try to measure the change in delta G. It's not as easy as doing it with delta H, but you could do it. But maybe you don't want to, or maybe it's actually not possible to measure it directly, right? So then what do you do? Well, Hess's law comes in handy because we can use other things that other people have already figured out, and we can just combine them to get the thing that we want, and then we can get the delta G for that. So there's not going to be ever a table that lists all the possible chemical reactions, right, and all of their delta Gs. Because for one thing, it would be super hard to find what you needed in there. So we're going to have some simple things like this where we might know delta G for the reaction. We're going to have lists in a table where different molecules have delta Gs of formation, and so we can use these techniques to estimate delta G. Any questions? Here's a great question. Why is free energy free? Well, it doesn't mean that you just get energy for nothing, because that doesn't happen. Many times we want to use the energy that's released by a chemical reaction to do some work for us, right? So we have combustion of gasoline in the car, and we're using the energy that's given off to move pistons in the engine and cause the car to move forward, right? So we're getting some work out of it. The change in free energy represents the maximum amount of work that is available or free to do the work. So you could look at a bunch of people, and some of them are busy doing something, and some of them are just kind of sitting around. It's like, hey, you could help me move chairs. You're free, right? Now, are all of them going to come and help? Probably not, but that's the maximum that you could have. So delta G is the most amount of energy that could be used to do work. Generally, that's less than the change in enthalpy. So if we have carbon and hydrogen and we form methane, delta H for the reaction is 74.6 kilojoules. That's the amount of energy that's released. But the maximum, the work that can be done from that is 50.5 kilojoules. This is smaller than this. We can't do 74.6 kilojoules because some of this is lost as heat to the surroundings, right? The engine in your car gets hot. That's energy that's being lost. Obviously, it's not disappearing, but it's not useful to us, right? So it's something that we can't use. So in most real reactions, you're going to have things like heat loss that are going to cause delta G to be smaller than delta H. Any questions? So the change in free energy is the theoretical limit of how much work can be done. You never hit the theoretical limit. So the laws of thermodynamics can be summed up this way. There's no free lunch. You can't get ahead. And this one says you can't even break even. So really, really encouraging there, huh? In a real reaction, we have less energy to do work because energy is lost to the surroundings as heat. Only a reversible reaction can reach the theoretical limits. That's one where a teeny tiny change can cause it to change in direction, and that's because it occurs infinitesimally slowly, and the free energy comes out in teeny tiny increments. Now, is that going to be useful to do work? No, it's not. That's just theoretical. So this is a reversible process. Here we have sand sitting on a movable disc here, and it's supported by gas underneath. So we have some sand on here. If we take off one teeny tiny piece of sand, this mass is going to be a little bit less, and this platform will go up a teeny tiny bit. So one at a time, you take sand grains out of here, and this platform is going to go up. Are you going to even be able to notice the change? No. Teeny tiny changes. The weight of sand is going to match the pressure at each increment. And then you could take the sand and put it back on there piece by piece, and it'll go back to where it was. That's an example of a reversible process. Highly idealized. Any questions? Real reactions are irreversible. They are not reversible. They do not achieve the theoretical limit of available free energy. So here we can think of a battery has stored energy in it. And we can take energy from the battery to run a motor, right? We can use that motor to charge a battery, right? But in the process of taking this energy to run the motor, we're going to lose some of it as heat. And when we take this energy from the motor and go to recharge the battery, we're also going to lose some to heat. So the amount of energy needed to recharge the battery is more than the amount of work that got done. So we lost some stuff here. We didn't break even. We lost some energy. And one way we can think of this is as a heat tax. So every time, I think I'm getting ahead of myself. No, maybe not. Every time we change energy from one form to another, we're going to lose some of it as heat. And so, that's why you can charge the battery and then do the thing, but it's going to take more energy than the work you got out of it to charge the battery. We've got a permanent dispersal of energy to the surroundings. Sometimes we refer to it as being lost. It's not lost in the sense of it disappeared or it's gone. It's still in the universe, but it's not useful to us anymore, right? So in that sense, it's lost. If we look at a chemical reaction with a positive free energy change, then that's the minimum amount of energy needed to make that non-spontaneous reaction happen. The minimum. You're going to need more.